The free-falling objects actually represents one-dimensional motion along the y-axis, which represents a uniform motion with an acceleration that is due to the acceleration of the gravity. The free-falling object is actually falling under the influence of gravity only, regardless of what is the initial velocity of it. The ideal case of this motion occurs when the air resistance is negligible. Here we have to assume that only one force acting on the object while it's falling, that is the force of gravity. As Galileo discovered that when two objects dropped simultaneously from the Tower of Pisa, he found that they hit the ground at approximately the same time, regardless of the mass of the object.
We are used to seeing light objects fall more slowly than heavy objects. But why do light and heavy objects fall differently? We will use this pair of tubes containing metal and paper discs to show the effect of eliminating air resistance. This is how the objects fall when the tubes are filled with air. If we now remove most of the air from the tubes with a vacuum pump and repeat the demonstration, the results change dramatically.
There are three different cases of interest to be considered in here. If the object is released from rest, which means that the initial velocity is zero, and then the object is thrown downward with an initial velocity, and finally when the object is thrown upward with an initial velocity. In free-falling bodies, two assumptions must be made. That is, we consider the acceleration in the direction of the free falls equal to the acceleration due to gravity and approximately constant. Obviously, as you know, the acceleration due to gravity changes as the latitude change above the Earth's surface. But here the assumption will be made that all the cases you're going to handle are at the Earth's surface. In this case, the acceleration AY along the y-axis is equal to minus g, where g the acceleration due to gravity, which has a magnitude of 9.8 meter per second square, and we also put it approximately equal to 10 meter per second square, and the air resistance here in this case is negligible. Here the equation of motions in one dimension with a constant acceleration considered previously, we're going to use them here by replacing x by y. And the first equation is for the final velocity as a function of time, where the second is for the displacement, where all the other constant and variables are considered except the acceleration. And the third is all the variables and constants are considered except the final velocity. And here finally all the variables are considered except the time. And as shown in the figure, that the acceleration due to gravity is downward. Doing that, we have also to replace ay by minus g in the equation. And then we're going to get the final as v initial minus g, the acceleration due to gravity multiplied by the time. And the second equation, the displacement equal v final plus v initial over 2 and multiply by time. And the third equation, we have delta y equal the product of the initial velocity and time minus half g t square. And finally, the square of the final velocity equals square of the initial velocity minus 2g delta y. Obviously, the minus sign of the acceleration due to gravity is already introduced in the equation, where delta y in these equations must be also considered, depends on the direction of the motion. In here, the object, if the object is moving upward, then the velocity, the initial velocity, must be considered as positive, and delta y as well. As you see, the arrows indicate the direction of both the velocity, initial or final, and the displacement. This is in the case that the object is still going upward in both cases. Now, in the other case, if the object is moving downward all the way, then the initial velocity and final velocity may have a minus sign, while the displacement is going to take, of course, minus sign as well.